So I'd like to bring up our next presenter. John Min is the Director of Solution Engineering at Andis USA. He has an extensive background in processing, CPU, DSP, and ASSP. Prior to Andis, John spent the last 30 years in processor companies like Sci-Fi, MIPS, and ARC in various technical roles. He also worked in the consumer electronics space at LG and HP. And John has degrees in biomedical and electrical engineering from the University of California, Southern California, excuse me. And his topic presentation is Andis is Driving On. Andis is expanding RISC-V application space with ASIL Certified Cores, and they will be introduce the industry's first ASIL Certified RISC-V Solution for Automotive Applications. Please welcome Mr. John Min right here.
Thank you. Green button. Thank you. Hi, good morning. It's very nice to see all of you. Some of these events become more like reunions to see old friends. Glad to see you all made the end of the world. So, to talk about what the topic of this is, Andis Driving On. It's pretty simple. I'm going to talk about the cores that are available today for our customers to license and use. We'll talk about market overview a little bit. Charlie went over some of our company vision. I'm going to be more practical to say what you have today. We'll talk about the architecture. We'll talk about some of the cores, little differences. And lastly, we'll end with our N25F SE, our safety certified, ASIL B certified core. Andis is firing all cylinders. The RISC-V world, to divide the computing world into 4 different segments, we've been very strong in more embedded processors. So where end users control the software, they configure the CPU with the right features. We're really strong. The second market we as Andis and RISC-V is getting into, it's more general purpose microcontrollers or signal processors. Third market is more DSP, vector-centric processors. I know because I did my master's in DSP and there are no DSP-specific chips anymore. CPU has taken over this function. The fourth market is application processors. Now, this is where end user interacts with the computer in a very interactive way, and software may not come from the end user or the device manufacturer. Software comes from a third party. So, Andis has been working really well, diligently, working from lower left to the upper right. So, the quick history of Andis, we're a pure play CPU company. We're CPU specialists. We have architectures starting from version 1 to version 3 was Andis specific. And we have multiple cores. And since the early beginning of RISC-V, we've been very involved. And we have an architecture called Andis V5, version 5. And we'll talk about what the differences are. But our history-wise, we had our own architecture. We've been innovating, and we've adopted RISC-V. So for RISC-V, for Andis, RISC-V is a starting line. Our cores are fully RISC-V standard. We're RISC-V cores. We have all different extensions. We have high performance floating points. We have DSP extension, RISC-V-P extension, and then we've been supporting vector extensions and MMUs for applications. So, Andis is RISC-V, but however, we're a little more. We have Andis baseline extensions to accelerate compute, accelerate branches, and sign extensions, and lastly, to reduce code size. And the RISC-V-C extension does pretty well in reducing code size to 16 bits. We could go a little further than that for the applications where code size is very important, more important than absolute performance. So we're RISC-V plus a little more. And lastly, we have these performance extensions that either improve performance, improve security, improve reliability. One is we have a technology called StackSafe. Second one is a power break and quick nap to manage the power consumption of the processor. So we all know what DVFS is. You could control the function of the processor externally by controlling the clock. Well, we have a technology to do that in software. If I know I'm going to wait a while, maybe I'm polling a slow device, I could slow down the pipeline so I don't have to execute no-op really fast. We have different technologies. Lastly, we talked about code dense to reduce code size. So we could improve reliability with stack safe, watching the stack size. We could improve code density, memory usage, and lastly, improve power. So we have all these advantages built on top of RISC-V, which is great already. And lastly, we have something called Andes custom extensions. Basically, you could create a domain-specific processor. Okay? RISC-V is great. You can configure it for different extensions, different instructions, different features. But we could go one step further in creating application-specific processor. We have a core. We have a technology called Andes custom extensions that could interface with coprocessors. Some of you I know from my previous life, different processors had a coprocessor interface, dedicated processor interface to talk to an external agent. We have something even better than that. I could create custom instructions. Sure, that's great. I could create a better multiplier, better bit swap instructions. But I could do even more than that. I could create complex instructions. What if I could give you a matrix multiply instruction? I could do that with custom local memories. Or I could talk to external accelerators, create specific memories and buses that could move data in and out. And we use this for our vector technology that accelerates performance as well. We'll talk about that. And we marry it with a great tool called Copilot that walks you through prototyping instructions and testing and finally implementing those instructions. And nice thing about our methodology is it's self-checking, creates automatic verification environment. Okay. Here's a quick example of vector product with 64-bit, 8-bit data. Left is our ACE instruction format. It's very simple, no specific language to learn. Few keywords, and I write my Verilog code, and I could just compile and run it, and eventually I could get almost 80, 90 times acceleration of this specific application. This will yield to about 20, 30% acceleration overall. And generally, when you create a custom instructions, custom memories, you want at least 10x acceleration to 100x acceleration of that algorithm. Let's talk about the cores that implement all this. And we divide it into a few fields. We have entry-level core, N22. I joke this is 8051. Okay? 8051, we know will never die. Intel did a really great job creating it. But we have our own 8051 called N22. This is one of the smallest useful RISC-V microcontrollers on the market. And then we have the 25 series, which is a 5-stage pipeline, kind of sweet spot for embedded processing, both in terms of speed and power. And that comes in multiple flavors. Our flavors is embedded control, DSP, vector math processing, lastly, application cores. And we'll talk about 27 series. That MemBoost is important because it accelerates it's the first one of the building blocks that moves from embedded cores to more higher performance cores. And then we'll talk about the 45 series, which is a superscalar processor available in both control and application cores. So our NX27B is first RISC-V vector processor. D25F is first DSP core. And lastly, most important core we're announcing today, N25F SE, which is industry's, I think is the first certified, ASIL B certified RISC-V processor in the market. So let's talk about a few cores. So N22, as I said, is our 8051 smallest standard core and supports RV32E and I. And it's a 2-stage pipeline. It's a simple processor, very small, but very powerful. We do branch prediction, multiply as an option. So there's a lot of optional components to really create that small microcontroller, including local memories, and then the small caches in case you're executing out of flash. Now, I'd like to meet somebody who's using 512 megabytes of local memory. We could do it. I'm not sure anybody's actually done that big of memory. And 25 series microcontroller, the key thing is pipeline gets deeper, so you could run faster, so you get more megahertz. Second thing is this has features for local memory and the full caches, IND first level caches. So it becomes more of a processor, but we have a microcontroller variant. And then we move up, use these cores as a building block. We have D25F, which includes the RISC-V Extensions. So this is the N25 plus P extensions. So in a way, you get we enhanced the 32 by 32 multiplier into dual 16 or quad 8-bit SIMD operations. It has all those nice features: PMP, stack safe, power break, and bus interface wise, we could talk to HB or AXI. Now, here's some of the performance gains we could get over our competition. Cortex M4 and M7 are sort of cores out there that we compete with. Our SIMD unit is very powerful and very efficient, so we could get the 2 or 3x performance of our competing cores. And other instructions are available, RB32 or RB60. Okay. The vector processor, now this is one of the exciting cores. It was very popular. We built on the 25 series. So it's a NX27V, the 64-bit 5-stage pipeline core. It has memboost. We'll talk about what memboost is. We had to put in the system. In a way, compute was easier than moving data. We could compute really fast, but then we always had to wait for data. Processors have caches to overcome this. For vector unit, moving data is the key. Data format would support all the int8 to int64 and floating point 16 to 64, and we support bfloat 16 in for AI format. It works really well. And two things. We improved the data flow. One way is a brute force method. You could have up to 512 kilobytes of data cache, which is fairly large data cache, but that's what's needed if you really want to run the vector unit at really high performance. Well, that's a brute force method. That's what I would do. Charlie here is a little more elegant than I am at my company. So we created this steering port. Remember, we had the custom extensions, ACE custom extensions that could create custom instructions, custom memories, and custom ports. Well, what if we created something called steering port using my custom port methodology? And since my vector unit could be 512 bits or 1,000-bit vector, what if my bus width matched my vector width, my compute width? And I could have a special, very high-speed accelerator port to talk to the vector unit. So we're using our ACE capability to create the steering port matched to my vector unit to move data in and out of the core to optimize compute. The idea here is I have the vector unit, I need to do a lot of AI or calculations, and I want to minimize stalls due to memory operation. So we call it steering port. It's been very popular. Allows you to have much higher bandwidth to feed the vector unit. Now here's some of the sort of acceleration data. With element to 32, we're seeing anywhere between about 10x to 100x acceleration of different algorithms. We do very well in floating point operations, floating point 32 adds, matrix multiplies, CNN, other operations. And our vector is very configurable, so end users could choose to optimize for the right hardware, right software to the right performance. So let's talk a little more the application cores. Now, these are application cores that could run Linux, And we have the 25 series, which is really good, compact, single-core Linux unit. We have a multi-core variant. You have a multi-core Linux applications. So these are sort of more embedded oriented. And then we have higher performance cores called 27 series. If you remember, think back a few slides ago, my vector core is NX27. So one of the few key features that are different between 25 series and 27 series is something called MemBoost. MemBoost is a memory technology to accelerate memory movement. One is data cache write-around. This is useful when the data is passed from the processor to a peripheral or a different processor. CPU might not use that data again, but you want to pass it along. Then we have instruction and data prefetching. It's nice. If you're doing linear computations or actually linear processing, it's very useful. Every fetch brings in more instructions. Every data read brings in more instructions as well. Third thing that we do is outstanding out-of-order memory requests, multiple memory requests on the system. So I could talk to a slower peripheral and fast memory at the same time. And lastly, we're going to have dedicated R&D buses, more bandwidth. We always strive for more bandwidth, and we could deliver that for you. For vector core, these 4 technologies came along with our vector core to improve the memory bandwidth, memory operations. But now we have it in the application cores as well, because application cores have our DSP SIMD implemented. And eventually, you could see vectors being implemented with application core. So now these are the building blocks. Our high performance cores, 45 series, comes in all different flavors as we saw before, embedded, DSP, and applications. It is a high performance dual superscalar in-order core, and it's available both 32-bit and 64-bit cores. DSP extension is optional, so all these cores come with SIMD unit, or can come with SIMD unit. Multi-core support L2 cache as well. Now, one thing key to look at is it has 4x performance to previous 25 series cores. A lot of the performance gained from MemBoost and also being superscalar. Multi-core, we could have up to 8 multi-core implementations with the L2 cache controller as well. So now we are marching our way up to a higher performance Linux and application cores. So lastly, we're using all these building blocks, and now the next market that we're attaching, with it embedded, with the DSP, with the general purpose microcontroller. Now the 4th block, application cores or automotive cores we're working on, functional safety. So it is fully certified for ASIL B with SGS. We've been ISO 9001 certified for a long time. And N25F, our embedded N25 series controller, has been safety enhanced and certified. And it has full ISO 262 compliance. And full safety package is available for this core. I think Charlie announced that we have 7 customers already for this core. So we are driving into more different spaces. So we're in the in-cabin radars, auto TDI, MCU, and auto storage. And hopefully we'll be expanding into more markets. And these are ASIL B certified, dashboard, car monitoring, keyless systems, tire pressure monitoring, ADAS applications. Okay. We are considering ASIL D applications. As Charlie mentioned, we'll be introducing at least 1 ASIL certified core per year. And I think what Charlie's not saying is that's probably how long it takes to do the paperwork and certification per core. There's a long time, and I'm glad it takes a while to go through the full systems. So, I have to take out this slide. Here's some examples from vendors. ASIL B is doing instrument clusters, infotainment, navigation, lighting. ASIL D eventually will need engine control drivetrain. One example I use is emergency braking system. That's going to be ASIL D, and we'll be addressing those markets with the future core releases. Right now, we're looking at more ASIL B applications. Okay, so that is a preview, or that is a quick overview of the cores that we have today, and the ASIL B certified core that's been announced. Thank you.
Thank you. Thank you, John Min. All right, everyone, what we're going to do is take a 1-hour lunch break, and we will be back in the room at 1 p.m. Thank you so much.